Students, suppose we take a wooden block with the iron filings on it, which is shown over here, and then we pass a wire through it and we connect it in a circuit. And then if we apply potential difference, when current starts flowing, you will observe that these randomly placed iron filings arrange themselves in concentric rings like this. So, why does this happen? The answer is electric current applies magnetic field in its area. So, as you might have guessed it by now, that today we are going to start with the new chapter, magnetic effect of electric current, which is chapter number 13 of the textbook. And what we are going to study today? Today we are going to study introduction of the lesson, and we are also going to study magnetic field and field lines. So this is part number 1 of the lesson. Let us see first the introductory section of the chapter. First of all, in electricity chapter, we studied about heating effects of electric current. And today we are going to learn magnetic effects of electric current. In fact, in this complete chapter we will be studying magnetic effects, different magnetic effects of electric current. The electric current produces a magnetic effect. So, if you consider a circuit and if you pass a current through the circuit, for example, in this case here there is a positive, here there is negative, so current will flow in this direction. Now, if you place a cardboard in between, or if you place a magnetic needle in between, you will observe that whenever you switch on the circuit, magnetic needle will show the deflection. What does it imply? That there might be a magnetic field produced by current which is deflecting this magnet. Otherwise, there is no reason why it will deflect. Okay, if you place it somewhere else in some isolated place, you will find that it will always align in north-south direction. Magnetic needle always align itself in north-south direction. When will it show deflection? Only when there is a magnetic field around it. And think the fact that this needle shows deflection when electric current passes through the circuit, it only implies, it only tells us that current might be producing magnetic field around it. Students, this was not realized, this was not found out until Hans Ørsted, a scientist, discovered this accidentally. We are going to study that in detail, but let us now continue with the points. So thus we can say that electricity and magnetism are linked to each other. The conclusion that we can draw from this experiment is that electricity and magnetism is somehow related to each other. Then in this chapter we will study these magnetic fields and such electromagnetic effects. We shall also study about electromagnets and electric motors, which involve magnetic effect of electric current, and electric generators, which involve the electric effect of moving magnets. So the thing is, just like there is magnetic effect of electric current, that is, electric current produces magnetic field which affects other magnetic field, right? Similarly, a magnetic field also affects electric current. So in a way they both affect each other. So you can say that they are two sides of the same coin. Now let us see the man who was behind this theory. His name is Hans Christian Ørsted. Hans Christian Ørsted, one of the leading scientists of 19th century, played a crucial role in understanding electromagnetism. I would not be wrong if I say that this theory, this electromagnetic theory, would be lagging behind if Hans Ørsted was not there. In 1820, he accidentally discovered that a compass needle got deflected when an electric current passed through the metallic wire placed nearby. Initially, even he didn't realize why the magnetic needle was showing deflection, but eventually he realized that only when current flows through the circuit, only then it showed a deflection. So, after realization, through this observation, Ørsted showed that electricity and magnetism are very much related to each other. His research later created technologies such as radio, television, fiber optics, so various technologies that we enjoy today is because of this theory. In honor of Sir Hans Ørsted, the unit of magnetic field strength is named as Ørsted. Well, now we will see a new topic, magnetic field and field lines. So, we are familiar with the fact that compass needle gets deflected when brought near a bar magnet. We know this. And why does it deflect? Because it is a magnet itself. So this compass needle is also a small bar magnet. The ends of the compass needle point approximately towards north and south direction. Why do they point towards north and south direction? The reason is Earth itself is a big, vast, gigantic magnet. Okay, and because of this law of attraction between opposite poles, the south pole of the needle gets attracted towards north pole of the earth, and the north pole of the needle get attracted towards south pole of the earth. So in fact, this end that points towards north is called as north seeking pole or north pole simply, and the other end that points towards south is called as south seeking pole. So that's how the needle gets aligned itself in north and south direction. We already know that like poles repel each other, means north and north pole they will repel each other, whereas south and south pole will also repel each other, and unlike poles only attract each other. So north and south attract each other. North and north or south and south, they don't attract each other, they repel each other. Let us see next few points. Iron filings on sprinkling over a magnet arrange themselves in falling shape. And what is that shape? This is that shape. If you sprinkle iron filings, you will observe that they align themselves in this particular shape. Why do iron filings arrange in such a pattern? And what does this pattern demonstrate? That's what we are going to learn today. The magnet exerts its influence in the region surrounding it. And this field of influence around the magnet is of this shape. Now, if you observe this diagram very closely, I will just try to magnify it. You will observe that this north pole and south pole, their field lines are very close to each other. If I call these lines as field lines, then they are very close towards north and south pole. What does this imply? This implies that the magnet and its magnetism is stronger at the poles. Okay. To conclude, we can say the magnet exerts its influence in the region surrounding it. Let us move on to the next point. The force thus exerted makes iron filings to arrange in a pattern. The region surrounding a magnet in which the force of the magnet can be detected is said to have a magnetic field. I repeat, The region surrounding a magnet in which the force of the magnet can be detected is said to have a magnetic field. Then the lines along which the iron filings align themselves represent magnetic field lines. I repeat, the lines along which iron filings align themselves represent magnetic field lines. I will just show you a diagram. So this is one magnetic field line. I repeat, this is one magnetic field lines. So like this there are many, in fact countless you can say. There are many magnetic field lines around magnet. The noticeable thing about this diagram is these magnetic field lines are very close to each other near poles. It implies that north pole and south pole of the magnet, they have a stronger influence. So that area around the poles has a strong magnetic influence. Then magnetic field is a quantity that has both direction as well as magnitude. So in a way it is a vector quantity. The direction of the magnetic field is taken to be the direction in which north pole of the compass needle moves inside it. Therefore, it is taken by convention that the field lines emerge from north pole and merge at the south pole. So here if you have a closer look, you will observe that magnetic field lines have emerged from north pole and arrow indicates its direction towards south pole. So this is how magnetic field lines work. They emerge from north pole and merge at the south pole, but this is as per sign conventions. In real life you won't see any arrow. Then inside the magnet the direction of the field line is from its south pole to north pole. So inside the magnet the situation is exactly opposite. Here field lines are shown from south pole to its north pole. So that's how magnet works. Thus magnetic field lines are closed curves. Okay, they are closed curves, they are not open curves, though you might feel that these are open lines. No, but here somewhere they are going from north pole to south pole, and inside it is going from south pole to north pole. Here we cannot show it, all the lines we cannot show, but they are there. So magnetic field lines are closed curves. Well, the relative strength of the magnetic field is shown by degree of closeness of the field lines. So if you want to show that magnetic field is strong here, then you have to show the lines close together. The field is stronger, that is the force acting on the poles of another magnet placed is greater where the field lines are crowded. So that I already told you. Wherever you will find that the field lines are very close to each other, if they are crowded, that implies that magnetic field is strong over there. The next point is no two field lines are found to cross each other. You will never find this, that the field lines are crossing each other, they are intersecting each other. That never happens. They might come close to each other, but they won't intersect each other. And with that we come on to the last point, which says if they did, it would mean that at the point of intersection the compass needle would point towards two directions. What does it imply? Suppose in your wildest imagination, if you try to consider that these lines are intersecting each other, then what would happen if I bring compass needle in such cases? If I bring compass needle in such point where lines are intersecting each other, then you will see that the needle would point towards two directions, which is not possible. Okay, so this implies that magnetic field lines would never cross each other. Well, that was all for today. With this we come with our to the end of the presentation, which is assignment. So the first question is, why does compass needle get deflected when brought near bar magnet? Then second question is, can we separate the poles of the magnet? Now students, the answer to this particular question, question number 2, you might not find it in this presentation. In fact, I have not asked it from the presentation, but I want to check your understanding. So you have to simply say yes or no. Can we separate the poles of the magnet? Okay, you don't have to give any reason. If you know, well, it is good, you can give it, but it is not compulsory. Then third, name some applications that use magnetic effect of electric current. It might be electric motor, electric generator. There are various applications of magnetic field, effects of electric current. You have to find some and mention them. And the last question is, draw magnetic field lines around bar magnet. You have to draw the diagram of magnetic field line. Well, that was assignment for you. If you have any doubt, feel free to ask. See you in next session. Until then, take care. Bye bye.